Yeah. All right. We'll wait for a second while the snowplow goes by my building. Before I begin, I'd of course like to thank the organizers. Thanks, Lewis, for having me, and thanks all y'all for showing up. I know the last minute time changes makes things a little confusing. So today I'm going to be telling you about some joint work. I think the main theorem of which is in progress with James Farre about random hyperbolic surfaces. And in particular, it is about a conjecture of Mirzakhani and a generalization thereof. Here's sort of the plan for the lecture. And I actually want to tell you a little bit about the main theorem before we get into anything, because we're not actually going to see the statement of the main theorem until 45 minutes in, unfortunately. But so the sort of main idea of the talk is that we'll see that equidistribution results in flat geometry, whatever that means, imply equidistribution results in hyperbolic. So for those of you who were here last week, Sahana talked a little bit about, there are these similarities between these combinatorial triangulated surfaces and random hyperbolic surfaces. Here, I'm going to be telling you about similarities between flat surfaces and hyperbolic surfaces. But more than that, just that, I'm going to be building a bridge that allows you to take theorems, honest, legitimate theorems about flat geometry, and turn them into theorems about hyperbolic geometry. All right, so let's go ahead and get started. So I should, before telling you about how you build random hyperbolic surfaces, I should tell you what is a random hyperbolic surface. So of course, there are many different ways that you could define a random hyperbolic surface. And we saw one of these last week. So I'm gonna tell you about a different one though today. So throughout the talk, S will be a closed surface of genus G greater than or equal to 2. And so by the uniformization theorem, right, we can think about the space of complex structures on S as the same as the space of hyperbolic structures on S. And by a hyperbolic structure, I just mean, if you want, it's a representation of S as the quotient of the upper half plane by co-compact group action. All right, and for a fixed G, the space of all of these structures is packaged together into a nice deformation space, a nice moduli space. Which, if you want, which I'm just going to call MG, will be the space of hyperbolic surfaces of genus G up to equivalence. But, well, MG is rather complicated. And so oftentimes it's nice to, not just consider MG, but it's nice to consider MG together, a hyperbolic structure together with a little extra data. And so we'll introduce the Teichmuller space as well, which is the space of thinking about, again, a hyperbolic surface as the quotient by a group. It's a space of discrete and faithful representations of the fundamental group of your surface into PSL2R. I guess I should probably say orientation preserving, but anyways. And again, this is up to the natural equivalence, which is conjugation. And the reason that we like to consider this space as well is because it's naturally related to the moduli space. In particular, it's the universal cover in the orbifold sense. So oftentimes, if we want to think about objects living inside of moduli space, it's oftentimes better to just think about objects or structures on Teichmuller space and then show that you can quotient down to push them down to moduli space. All right, but so this is our space. This is our space of hyperbolic structures. And I want to tell you what a random hyperbolic surface is. So how do we actually specify one of these? Right, I want to be able to say, here is a point in moduli space. So Sana talked a little bit about this last week, but I'll just remind you. There are natural coordinates for Teichmüller space, and not as night. So this is one of the reasons that we want to think about Teichmüller space, called the Fenchel-Nielsen coordinates. So if you fix a hyperbolic surface and you fix a Pants decomposition on it, which is a set of simple closed curves cutting your surface into threefold spheres. So if I focus on this one right here, we have a sphere with 1, 2, 3 boundary components. Then the hyperbolic structure on this, or the hyperbolic structure is exactly determined by data that's recorded by this Pants decomposition. So in order to determine the hyperbolic structure on a pair of Pants, all I need to do is tell you what the lengths are. So in particular, if I have 3G minus 3 curves in my Pants decomposition, then I need 3G minus 3 lengths. And well, that's enough to determine the space of structures on the pairs of Pants, but now I have to tell you how to put them together. And so I need to also specify a parameter that tells me about twisting. So this will be an arbitrary real parameter, and this will be some twisting data, which I'll write as Ti. So in particular, Teichmüller space is it's a cell. It's a, sort of topologically not all that interesting, even though moduli space is very interesting. And so this is how I specify a point in moduli space. But again, I want to specify what does it mean to be a random point of moduli space. And the way that I'm going to do this is that I'm going to say, well, random means generic with respect to some measure. And so the natural measure, the measure that we're going to put on moduli space is actually really nicely related to these coordinates. Oh, oopsies, to the Fenchel-Nielsen coordinates. Because these coordinates are not just nice, they're in fact Darboux coordinates. So there's a natural symplectic form called the Weil-Petersson symplectic form, which we don't really need to know what it's called, what it means, but you can express it in terms of coordinates by d length, wedge, d twist. This formula is due to Wolpert. And in particular, from a symplectic form, you can take the top wedge to get it measured. And so the thing that we're really going to be interested in is this measure, the Weil-Petersson measure on Teichmüller space. And in fact, this is invariant under the mapping class group. So we also get a measure on moduli space. All right, and this measure is in fact finite volume. So it's up to normalization and probability measure. And so we can actually, pick a random point or talk about what happens for a random point of Teichmüller space, of moduli space, et cetera.
I think I objected. How do you pick a random point of Teichmüller space? Isn't it an infinite?
No, yeah, you're right. We can talk about a random point of moduli space, and then I guess if you want, you could take a random element to the mapping class group.
Okay.
But, yeah, right. So you can take out your copy of moduli space out of your back pocket, and then you can throw a dart at it, and then you can take, with respect to this measure, you can take a random point with respect to this measure.
Yeah. Okay.
Yeah. Fair enough. All right, but in fact, this is not the measure that we're going to be considering, even though it's a very nice and very reasonable measure. And it's because I'm going to, for reasons that we'll get into in 10 minutes or so, I'm going to want to consider a weighted version of this. And so the measure that we'll call Mirzakhani measure we'll define by some function, which is TBD. This is some function that depends on the hyperbolic structure, depends on the hyperbolic surface. And that will weight, or will give a density to Weil-Petersson measure based on this function. And we'll see why we do this in just a second. I guess importantly, this function that we're going to be multiplying it by will be L1. And so the measure, the Mirzakhani measure is in fact also finite volume. But it is unbounded, and in fact, it's L2. And this is a result due to Francisco and Jaidev Athraya. All right. And so finally, this will be the measure that we actually want to consider. So we want to take a random surface with respect to this Mirzakhani measure. So normally, right, we'll be focusing on points where we'll be focused more on points where this density is higher than for Faye-Peterson. All right, and so I can tell you now that we've talked about what it means to be a random hyperbolic surface. I can tell you sort of the conjecture about twist tori and random hyperbolic surfaces. So the twist torus conjecture of Mirzakhani, which she never wrote down, but it is a problem that has been attributed to her in the literature and that I guess she would say at conferences. But it is the following. Fix a Pan's decomposition P. Any Pan's decomposition, and set all of the lengths of the Pan's decomposition equal to each other, or all the lengths of the curves. So all of your Pans look something like, going to be very regular, all with length L, and so necessarily they will have a symmetry to them. Okay, and so we've specified some lengths, and what we're going to do is we're going to take random twists in 0 to L up in 3g minus 3, because we want to glue each one of these Pans together along each curve with some random twist. And from this, we get an immersed torus in moduli space together with this is a torus, and we're going to take the Lebesgue measure, which we'll write as tau sub L, supported on this torus. And here I actually want the normalized. So it's sort of throughout the rest of the talk, we're going to only be considering probability measures. So we're going to sort of forget about any normalization constants. But anyways, we can talk about this a little bit more if you want. The conjecture, or the question, asks, does this sequence of measures, do these tori equidistribute with respect to Mirzakhani measure as L goes to infinity? All right, so you've got these immersed tori inside of moduli space, and as you take L higher and higher, they grow and they start to fill up moduli space. But the question is, well, do they go everywhere? And moreover, do they go everywhere sort of, with the correct frequency? All right, and so I can't give you a full answer to this, but just as mathematicians, one of the things we like to do when we can't fully answer a problem is to, think about a different problem. And Aaron, so, yes.
Is it possible at this point to say why the answer would definitely be no for the Faye-Peterson volume?
No.
And why you need the factor?
Nope.
The B, okay.
Yeah, so in the next slide, I will tell you why this, some other results which sort of look like this and show that this B should show up. And then in a little bit, we'll talk about what this B actually means.
Okay.
Yeah. So, I mean, first question is, is it even clear that, as L goes to infinity, these become dense in moduli space? And that is, I think, a priori, not at all clear. So. All right. So one thing we could do, though, before we get into, the meaning of this B function, is we can generalize this conjecture. And, instead of fixing all the lengths to be the same, we could fix some B in R to the 3g minus 3, some weight vector. And instead of taking all the lengths to be equal to each other, take B times L. So, maybe I want one curve to be length 1, the next one to be length 2, the next one to be length 3. And then as I scale up, I get, L, 2L, 3L, et cetera.
So Aaron,
yeah.
With the original conjecture where everything is fixed at L, the Kahn-Markovic proof of the Ehrenpreis conjecture I think it shows that this is going to be dense, asymptotically as L tends to infinity. Maybe I'm wrong. Sorry. I'm sorry. I spoke too soon because they're looking at finite covers.
Yeah, like if you get the finite covers, which are arbitrarily close,
yeah,
but it's not clear that you can push them down.
Okay, I'm sorry. Yeah.
It's a good thought though.
They do like really control what geodesics of length L kind of look like on a surface as L goes to infinity, don't they? I mean, well, anyway, maybe there's useful information there, I would think. But anyway, okay.
Yeah.
Sorry,
yeah.
Go ahead.
Okay. Well, I mean, the theorem I'll tell you will also sort of resolve this part of the problem too, but okay, and so we can take different weights, we can get different measures, and we can ask the same question for these measures, right? For some sort of measures based on other tori, of course. Okay, and so again, I want to tell you now a little bit about why is this conjecture even plausible, and why should this appear? And so the first result, sort of in this vein, is a result of Mirzakhani, unsurprisingly, that says if you take the Lebesgue measure on a set of X in Teichmüller space such that the length of all of the curves is less than or equal to L. And by here, I should say, I guess Lebesgue, really, what I mean is sort of Faye-Peterson. This converges to Mirzakhani measure, which I'll remind you is this weighted version of Faye-Peterson. And so if you're trying to think about what this space looks like, which I think is a useful thing, right? So this is L1 norm here. So the sum of all of the lengths is equal to L. If we look inside the weight space, right? So L1 up through L3G minus 3, what this is saying is that if you take sort of this pyramid, right, that goes all the way down to the origin, and then you take random twists over this, right? So this is the length space, and we also need to take random twists in the twist space. Then this converges as you make L bigger and as you expand out, right? This converges to the Mirzakhani measure. And so here, this is one very natural family of hyperbolic surfaces that will end up converging to this desired measure. All right, and so there are other results in this vein. So there's a result by Francisco Arana Herrera and also Mingken Liu, who proved that if you take the Lebesgue measure or Faye-Peterson on the set where the L infinity norm is at most L, then you converge to Mirzakhani measure. And so these are sets inside of the length space again that look like cubes, right? Because this is your L infinity norm. I should say also that they both did much more general shapes as well. Of expanding sets, but L infinity is just a nice one to draw. But something to note is that both of these sets that we're showing are equidistributing are 6G minus 6 dimensional. So you sort of have the full dimension inside the weight space, right? You have 3G minus 3 dimensions in the weight space because you're taking a whole ball, then plus all the 3G minus 3 dimensions of the twist space. What the twist torus conjecture is asking, though, is, well, I'm going to take the line, L, 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 and I'm going to take this point on it. And I'm going to, send this off to infinity and all along this line. And I'm going to take random twists. And so this is a 3G minus 3 dimensional set. And do these converge to that very same measure? And so, well, the theorem that I want to tell you about gives some strong evidence towards a twist-torus conjecture in some cases and disproves it in others. So the theorem is as follows. This is myself and James. So we're going to define a condition on the pair of pants. We'll say that it satisfies delta if two of the boundary lengths sum to the third. All right, some very easily checkable combinatorial condition. And well, the theorem is that so long as no pairs of pants of S minus P specifically, so only the complementary pairs of pants. We don't care about every single pair of pants, only the ones that are coming from sort of the pair of pants that's defining our twist torus. So long as none of these satisfy this condition, then yes, in fact, these generalized twist tori do converge to Mirzakhani measure. With a big old asterisk right there. And I'll explain this in just a second. And otherwise, the answer is no. So if some do satisfy delta, then the twist tori cannot converge to Mirzakhani measure, period. And these generalized twist tori equidistribute to, well, some measure, which is not in particular Mirzakhani measure. And again, this equidistribution theorem has a star next to it. All right, and so I should tell you, of course, right, if I'm going to tell you a theorem, I should tell you the caveat. And the caveat is that it's not for every L. It's in fact only along almost all sequences of T. And we're going to be considering this with sort of exponential scaling, and where L is equal to e to the T. All right, so this gives you a very large family of equidistributing tori, and it gives very strong evidence for the conjecture in one case and disproves it in another. But anyways, are there any questions about the statement of this theorem?
So like, it's conceivable, like if you were just, like there could be another measure that it limits to. I guess, I mean, like, when you say sequences of T, do you mean like, is T an integer, or is that just?
No, it means, yeah, so if I want to be precise here, what I mean along almost all sequences is I mean outside a set of T of density 0.
So it looks like you're going to do some kind of like a Cesaro average or something. So
yeah, in fact, the Cesaro averages do converge. And sort of what we're doing is we're just sort of pulling it out from that. And I'll say like this along almost all sequences, this is very much not the rest of the talk is going to be, I'm going to tell you how we get this theorem, in fact, from a much more general theorem, one that again takes theorems in equidistribution results in flat geometry and turns it into ones in hyperbolic. And so this artifact sort of along almost all sequences, and this, in fact, the scaling as well, the reason that we're using e to the T instead of just L is that we're, in fact, just proving a theorem in flat geometry and then pulling it back via this machine. And to prove the theorem in flat geometry, we have a lot of hammers that we can hit it with. But in particular, you get these caveats because of them.
Is it possible to say anything about this mu in the second bullet point? Is it supposed to be the same mu for any of these cases?
No.
Different
yeah.
Mus?
So in fact, depending on how many pairs of pants satisfy delta, you'll get different mu's.
But that's the only I guess that's the only
if every single pair of pants satisfies delta, then there is another combinatorial condition that can change what mu is. This will, I think that by the time that we get to the end of the talk, you'll have a good idea of what the mu's are.
If I sat here and thought for 5 minutes, would I be able to see why a plus b equals c causes mu to like miss some part of moduli space or something? Is there something obvious that I should think about a plus b equals c?
It's actually not clear to me if these mu, if you take their support, if it's actually dense moduli space or not. I'm not 100% sure of that.
Okay.
But the thing that you should be doing is looking at this picture. And maybe if you know some flat geometry, look at this picture and think about this picture.
Okay. Maybe
compare it to the picture for a plus b not is equal to c, and in particular if they're all equal, where your picture looks something like this. So I'll just leave those pictures up, and then you can puzzle over them before we.
Oh, sorry. What is the blue thing in the?
I'm not telling you.
That's a figure 8. Okay.
I'll tell you later.
Okay.
It's a suggestive drawing.
Okay. All right.
Don't worry about it.
Very mysterious.
I'm building tension. All right. So I'm going to answer your question from like 10 minutes ago, though, and I'm going to tell you what b of x is now. So I hope that I can, assuage your concerns by answering earlier ones. And to do this, I need to remind you of some things about the earthquake flow. So Francisco talked about this a couple of weeks ago, but I'm not going to assume that you were here or remember that. So I'll give you a bit of a primer for that. So the idea that we're going to end up doing is that, well, we've seen a realization of the moduli space of the set of all hyperbolic structures or hyperbolic surfaces up to equivalence. But we're going to, in fact, the b of x should in some sense be thought of as coming from the cotangent bundle of moduli space, in particular the unit cotangent bundle of moduli space. And we want to get some sort of hyperbolic interpretation of that. And that will tell us where our b of x comes from. So if we have gamma, a simple closed curve, or I guess any curve, in fact, but a simple closed curve is particularly nice, then it gives us a length function, right? A length function on Teichmüller space. Right? Given a marked hyperbolic surface, I can say what that curve is on that hyperbolic surface, and I can just measure its length. And in particular, because this is a nice function, we can also take its differential. And so we get, the differential of the length function is a cotangent vector. And so this gives us a way to realize certain cotangent vectors as hyperbolic objects. They're differentials of length functions. And a theorem due to Thurston is that, in fact, you can think about the entire cotangent space of Teichmüller space as a space of similar objects. So it's the set of x, right? This is the point in Teichmüller space, and the differential of some length function where not just a visible closed curve, though, but lambda is a measured lamination. All right. And so in particular, that means that we can write the cotangent bundle as to be homeomorphic to Teichmüller space cross the space of all measured laminations. So I should tell you what a measured lamination is, of course. So it's to be very imprecise, it's a generalization of a simple closed curve. So of course, here is a simple closed curve on my surface. And one nice measured lamination is, well, I'm just going to measure this. I'm going to give it a weight. And so I'm going to give it weight 2. This is a measured lamination. Or generally, though, they can be much more wild objects. So they can be objects which sort of spiral all around the surface and accumulate and have cross sections, Cantor sets, and all sorts of weird behavior. But they're still sort of nice generalizations of simple closed curves. And if this were a different talk, I would say more about the structure of them, and specifically about the structure of the space of measured laminations. But for this one, I'm actually not going to say much about this. I'm just going to tell you a couple facts about it, and you can ask me more about this if you'd like. So one of the nicest things about the space of measured laminations is that whereas the set of simple closed curves is sort of just a discrete set, right? It doesn't really have much structure other than, well, here are a bunch of curves. The space of measured laminations is in fact homeomorphic to a cell of the same dimension as Teichmüller space. It has a natural PL structure, piecewise linear structure, and an integer lattice inside of it. And so that the integer points are equal to integer weighted multicurves on your surface. And with all of this data, you actually get finally the most important thing that we're really going to want, which is a natural Lebesgue type measure, which we'll call the Thurston measure. And all right, so this is some space, it's parameterizing these objects. If you want, you can think about it as the cotangent fiber at a given point in Teichmüller space. And the sort of topological data of the fact that you've got this integral lattice gives you a way to think about the Lebesgue measure at each cotangent fiber. All right, and so what that means is that the unit tangent bundle, specifically of moduli space, once we quotient out, is we can think about it as the space of hyperbolic surfaces together with a unit length measured lamination. So notice I put that unit in. And so we're going to go ahead and call this P1mg. This will be our hyperbolic realization of the unit cotangent bundle. Moreover, this gets a finite measure because, well, the unit cotangent bundle of Teichmüller space had Weil-Petersen and Thurston measure. And so we're going to combine those two to make a nice finite measure on the unit tangent bundle. And what we'll call this is the Mirzakhani measure sort of on P1mg, which is going to be Weil-Petersen in the x coordinate, and it's going to be Thurston measure in the lambda coordinate. But here I've taken the unit length, so I need to sort of cone off my Thurston measure. And what this means is that, so here, this is the set of lambda where the length is equal to 1. And if I have a given set here, u inside of the unit sphere, then what I'll do is I'll just cone it off to get some other set u hat. And I'll just say that this sort of coned off measure of u is the normal Thurston measure of the cone off. So this is sort of a standard way to get a measure on a hypersurface from a Lebesgue type measure. All right. And so this I'm also calling Mirzakhani measure. And the reason is because of the following fact, which is, well, sort of just by definition, is that if we take the projection map from the unit cotangent bundle to back down to mg, call it P, and we take the push forward of Mirzakhani measure, this new Mirzakhani measure, well, we get the thing that I was calling Mirzakhani measure before, which was this B of x times the Weil-Petersen measure. So in particular, you can think about B of x, this is the volume of the fiber above a given point. So this is the Thurston measure of the set of lambda where the length of lambda on x is inmost 1. All right. And so, well, this is sort of, hopefully this answers your question, Jeff. Like, what is this B? What is this hyperbolic constant?
Yeah, thanks. That's great. So if you're far out in the cusp and you have like short curves, then this B will get big because you could add a lot of weight to that short curve, and that gives you a bigger region in ML. Is that right?
Yeah, exactly. Yeah.
Okay.
Yeah. So you can see that as you go out to the cusp, this B grows, unboundedly. Okay, and so the reason that I'm talking about all this is not just to answer Jeff's question, but it's that if you want to actually show equidistribution to this mu, this Mirzakhani measure, if you want to show equidistribution in MG, all of the results that I've talked about so far, really what they do is they actually show equidistribution. They lift up and they show equidistribution inside the unit cotangent bundle to this other measure, to this new Mirzakhani. And then you just push down and then you get the result that you wanted in the first place. All right. So this is the B, but I still have to tell you about the earthquake flow. Because, oftentimes in order to, actually show anything, to show most interesting things about equidistribution of measures, you're going to want a dynamical system. You're not just going to want a space with a measure on it. And so we need to introduce a flow. And so I'll just say that, right, if we have gamma, a simple closed curve, what we can do is we can earthquake along the curve by cutting open my surface along the curve, twisting, and then regluing. And so what this looks like is, I just duplicate this picture. Right, if I have a curve which is sort of passing orthogonally through my red curve, and I earthquake along the red curve, I will, sort of what I've done is I've shifted over by a little bit S. And so my earthquake flow along gamma, shifts by S. So I'm shearing. A good way to think about this is in the case when gamma is actually a subset of your pants decomposition, P. Because in this case, the earthquake flow is just translation in the Fenchel-Nielsen coordinate corresponding to the twist, because all you're doing is you're changing what the twist is as you're shearing. All right, and so I'm not going to tell you how to define an earthquake in general, unfortunately. But so in general, earthquakes look much more complicated because a measured lamination is sort of defined to be the limit of a simple closed curve. An earthquake for a general measured lamination, the earthquake along a general measured lamination is defined as the limit of twisting along simple closed curves. So and so, I mean, you might be worried because it's not obvious that this actually makes sense or defines, a nice hyperbolic surface at the end of the day. But I'll say that, it's since the 80s, I think it's been a sort of a well-established fact that, this sort of limiting process actually gives you a nice transformation of your hyperbolic surface. The point of this is that sort of from passing to just twisting in a curve to earthquaking in a measured lamination, you get a flow called the earthquake flow on P1MG, this unit cotangent bundle. And moreover, it's not just any flow, it's a particularly nice flow because, as Mirzakhani showed in 2008, this is ergodic with respect to the nice measure that we were considering before, this Mirzakhani measure on P1MG. All right, and in fact, this earthquake flow, this is the key tool, and really the thing that makes all of the arguments in Mirzakhani's results, Francisco results, and Minkun's results. All of these results that I've been telling you about equidistribution of hyperbolic surfaces, all of them use the earthquake flow as sort of in the key step. Right, but in order to in order to prove our result, we actually, so we very much do use earthquake flow, but we don't just use Mirzakhani's result. We don't just use the ergodicity with respect to this one measure, because again, I'm going to tell you that, well, you get equidistribution to other measures, and how do you talk about that if you only using ergodicity with respect to one measure? So in fact, what we do is we're going to end up sort of generalizing a lot of the machinery that goes into actually proving Mirzakhani's theorem in the first place, and then use that to get our equidistribution result. All right. And so before we do that, though, I need to tell you just a little bit more background material. So we've given a hyperbolic realization of moduli space and a hyperbolic realization of its cotangent bundle. Right. This is thinking about it as a space of measured laminations on a hyperbolic surface. But there's another very natural realization of MG that I talked about at the very beginning, right? It's a space of complex structures, or the space of Riemann surface structures on your hyperbolic surface modulo equivalence. And with this, there's actually a much sort of more classical realization of the unit cotangent bundle. And so we're going to draw inspiration, and in fact, we're going to draw techniques from that world. And so I'm going to give you a super quick crash course in quadratic differentials. So the space, this complex incarnation of the unit cotangent bundle, is the space of unit set area semi-translation surfaces. And so, well, if you want, what are these? These are polygons in the plane where sides are glued by a reflection or by translation, so here, or translation possibly with a rotation by 180 degrees, as we see here. And so this gives you a structure on a surface, and if you check, you can actually get a flat metric on the surface, except for the points that glued up at the vertices. So if I take this vertex, for example, and I trace it around, this side glues to over here, this glues to the bottom of this 1 hash mark, which glues to the end of the arrow, which glues to the left of the 3 hash marks, and so on. And if you count around, you'll see that, in fact, we end up with a cone angle here of 4 pi. And similarly, if we check around the other vertex by sort of the symmetry of this picture, we also get a cone angle of 4 pi. So we get a flat metric on our surface with a couple of cone points. And the space Q1MG is stratified by the number and angle and cone points that you get on the surface. And what we're going to be interested in is not necessarily the space, the entire space Q1MG, but a subspace of it called a stratum. And so a stratum, in fact, is locally, you can give it nice complex coordinate charts just by looking at how the edges of the polygon wiggle. These are called period coordinates sometimes. But in particular, the point of this is that you can take the Lebesgue measure on C of the n and pull it back to get a measure on the stratum, which we call the Mazur-Veitch measure. So Mazur and Veitch. And this is a very well-studied measure. People know lots of things about it, and it sort of serves as an analog of the Mirzakhani measure. Similarly, there is an analog of the earthquake flow on this side. And in fact, there's an entire SL2R action. So the space of polygons, right, is acted on by SL2R because, well, you just apply a matrix to the plane and take the polygon along for the ride. So for example, if I take 1101, I apply it to this, to the surface, I'm going to get something that looks like this or so. And so I can deform the semi-translation surfaces inside of a stratum by acting on it by one of these matrices. And in particular, we're going to be looking at the subgroup U, which is 1 star 0 1. So it's the shearing action, which is also sometimes known as the horocycle flow. All right. And so the reason that we're talking about this whole completely different system for a second is because unlike the system that I was just telling you about with the earthquake flow and the hyperbolic surfaces, this is much more well understood. So the reason that the Maser-Veitch measure is named as such is due to, well, this fundamental result of Maser and Veitch, which says that this horocycle flow, and so in particular the SL2R action, acting on the stratum is ergodic for every strata. And well, with the amount of time I have left, I'm not going to be able to tell you very much about the other dynamics, but let me just say that there are a lot. So in particular, there are Ratner types results for the SL2R action, which really say lots and lots of interesting things about the dynamics. And so you can really say quite a bit about what horocycle flow looks like. All right. So with all of that said, I've told you about the problem. I've told you about, well, here is this earthquake flow, which seems to be a good way to solve the problem. And then I started telling you about a completely different other flow. And you might be thinking, Aaron, what are you doing? You only have 10 minutes left in this talk. Why are you doing this? And the reason is because we have the earthquake flow, which is acting on this hyperbolic realization of the cotangent bundle. We have this complex or flat realization of the cotangent bundle, and the horocycle flow is acting on it. And in fact, these two actions, these two flows, are the same. And so it's a theorem of Mirzakhani and of James and myself last year that these two are squiggle. And so I should, of course, tell you what this squiggle means. So what Mirzakhani says is that these two flows are measurably isomorphic with respect to two specific measures. So with respect to this Mirzakhani measure we've talked about and the Maser-Veitch measure on the principal stratum. So the place where you all have cone points of angle 3 pi, and that's it. So on Q1, lots of ones. And as a consequence, because the Maser-Veitch measure is ergodic, the horocycle flow is ergodic for the Maser-Veitch measure, from this you get that the earthquake flow is ergodic for the Mirzakhani measure. All right. But so in my work with James, what we showed is that this map is in fact a Borel isomorphism. And so AKA it's a measurable bijection. So Mirzakhani's map was actually only defined almost everywhere with respect to these two measures, whereas our map is defined everywhere. And so what this means in particular is that you get a measurable isomorphism with respect to any measure or any horocycle flow invariant measure. And as a consequence, well, here you get lots of new ergodic measures for the earthquake flow. All right. And you might be thinking, well, maybe these two things are literally the same. You told me that both P1MG and Q1MG are the cotangent bundle or unit cotangent bundle, and these are both flows on the unit cotangent bundle. And so maybe, all we're doing is saying that, we're just looking at the same object in two different ways. But in fact, what you can show is that, well, there is no chance of being topologically conjugate. So this map that realizes this isomorphism is not continuous, and moreover, there is none. And this is the result of Francisco, Rana Herrera, and Alex Wright. All the same, I guess I'll just say one quick thing. In progress work, which is related to the thing that I'm going to tell you in just a second, this map, which I'll call O, is continuous, but with respect to a certain stronger topology. And so you can upgrade this to, I should be careful. I shouldn't say that you can upgrade it to a topological consistency, but the map is actually, it has many stronger continuity properties than just an average measurable map does. And on that note, now I can finally tell you that theorem that I said on the very first slide, which is about equidistribution. Because, well, here we were able to say these two things are exactly the same, or they are measurably the same. And so we're able to get measurable, sort of measurable results, right? We can get new ergodic measures because we can pull back measurable objects. And what we'd like to do is to pull back equidistribution as well. The thing you should be, very cautious about, though, is that equidistribution is a topological property. And so in particular, we have a non-continuous map. And so, well, if I wanted to think about weak star convergence, like how in the world do I talk about, what a continuity set is? How do I talk about what a continuous function is? So all of a sudden, my definition of continuous is different. All the same, though, the main theorem that I can tell you about is that you can pull back certain sequences of equidistribution results. So suppose you have some sort of convergence of nu n to nu, and these are all probability measures. On a stratum of QMMG. So this is some sort of equidistributing sequence of flat surfaces. And moreover, this limiting measure, nu, suppose that it's also SL2R invariant. So this is, that was the right thing I was supposed to highlight. This is a strong property, and it means that we have lots of very sort of important structure results about what nu actually looks like. So if this is the case, then in fact, you can pull back this equidistribution. So the measurable bijection gives you a correspondence of measures. And so you actually can say that the pullback measures, or if you want push forward by the inverse measures, O star and UN, they converge to O star and U on the hyperbolic set. So this gives you a way to take, results about flat surfaces and turn them into a family of results about hyperbolic surfaces.
So does this use the Eskin-Mirzakhani theorem about classifying SL2R orbits?
Yes, very much so.
Yeah.
So yeah, one of the things I flashed on screen really quick is that SL2R invariant measures are all supported on nice subvarieties of QNMG, and so you have a very nice structure to them. And you absolutely have to exploit that in order to prove this. Like, I don't think this is true, or at least I have no idea if this is true if you don't assume it's SL2R invariant, if you only think that it's Hoare cycle invariant, say.
Yeah. Interesting, yeah.
All right, so I know we started late, but I don't want to go too long. So with my last 2 minutes, I will actually switch to my prepared slides. And I will just tell you quickly how we actually can prove our twist torus-like theorem from this equidistribution result. So the idea is, well, we prove a theorem in flat geometry and we pull it back to the hyperbolic world. And so what you do is you define flat twist tori. And so this picture, I told Jeff to stare at a picture earlier, and this picture looks very similar to a picture that I drew before. And these are our flat twist tori, and that are glued out of cylinders of length of circumference L, and we can define a measure on it, nu, and moreover we can say that this nu is the same as the push forward of the twist torus measure on the hyperbolic side. And now we can hit it with a bunch of hammers in flat geometry. So in particular, using these Ratner type results of Mirzakhani Mohammadi and some work of Voronoi, you can say that, well, for most T, for a density 1 set of T, if you take the push forward of these measures under the geodesic flow, which is in fact just the same as the twist torus measure with a longer length, so you made your surface out of really long cylinders, then these in fact converge to the SL2R invariant, the measure supported on the orbit closure, whatever that is, of the twist torus. So it's converges to some measure supported on an orbit closure. And then the question is, well, what is this orbit closure? And then there are this very nice recent result of Paula Pisa and Alex Wright, which classifies these orbit closures. And so in particular, putting these all together, you get that the push for the sort of the pullback to the hyperbolic side of these twist torus measures, which were our original twist torus measures, will converge to the pullback of the orbit closure measure, which is in fact just Mirzakhani measure. And so really very much you use a lot of big hammers that are already extant in flat geometry. You prove a theorem with that, and then you pull it back using our machinery. All right, so I should finish there, but thanks for your attention.
Okay, thank you. So I guess I'll just open it up for questions.
Okay, so A plus B equals C. I guess you can't make a flat version of the picture that is in a sensible way or something. What is
well, you can. So, but if you do this, let's try to do this, right? So we have a
you're at infinity or something, right?
Well, so here we have A and B, and here's C.
Yeah.
And as soon as we try to build this cylinder, right?
Mm-hmm.
What we can do is we can glue sort of this bit to this bit, and we can glue this bit to this bit. And so what we'll end up with is a flat pair of pants that have, in particular, a double order 0 here. So instead of having 2 3 pi's worth of singularities, sort of our original flat pair of pants did, this will have a single 4 pi singularity.
Okay, so you're not in the generic stratum.
Yeah, so you're not in the generic stratum, and so your push forwards don't converge to the generic stratum, but they do converge up to a set of density 0 to that stratum measure.
Ah, okay.
And so in fact, what these other mu's are sort of pullbacks of stratum measures.
Okay. Oh, that's cool. Yeah, that's really cool.
So this torus that's in the space of quadratic differentials, can you describe it a little bit? Like if all of the lengths, all of the L lengths are the same, is it built out of cylinders in some simple sense? I don't know. I don't know how to. What?
Yeah, so it is exactly built out of cylinders, and so the way that I think maybe the best way to think about it is to think about it as gluing it out of pants. And so I claim that as soon as we need to sort of fix the height of the cylinder as well. And for normalization purposes, we wanted to have area 1. So let's go ahead and make the height of this cylinder
So the picture looks just like that. This and the 3 pi cone angles are the blue vertices.
Yes, exactly. Yeah. So the two 3 pi cone angles are.
Oh, okay.
Yep.
I understand now. Thanks.
Yeah. So you take the correct heights, and then you've got these pairs of pants, and then you just glue them
So,
together with
I mean,
arbitrary twists.
it seems like a non-trivial theorem that this really does correspond to the torus in the hyperbolic picture. I mean, well, I guess.
No,
I guess
yeah,
you just have to deform each pair of pants separately, and then.
I think the thing is, I didn't tell you how this map is actually, this map O that goes from the flat to hyperbolic side is actually defined. That's probably the bigger thing, right? You have to come up with the correct definition. And then once you have the correct definition, it's sort of built into the definition that it has to look this way.
I see.
But it's not, I think, Louis, what you're saying is it's not the case that if you glue together some of these things and then uniformize, you happen to get something that's in the torus on the other side, right? I mean, that's not going to happen. So you have to you define some map that kind of fixes that problem. Aaron?
Yeah, so in fact, right, this has almost nothing to do with the uniformization of whatever surface you get out here. So in fact, this map that takes P1mg to Q1mg, it will change what point you are at in moduli space.
Yeah. This came up in Francisco's talk.
Yeah,
although I guess
there
it's
are
a different map now, but
yeah, it's not even clear to me if there are any points which are fixed by it, by the map O. There are some like sets which are set-wise fixed, but I don't know, sort of because you can build things with lots and lots of symmetries that sort of have to be fixed. But it's not clear if there are any like specific points that are actually fixed.
Okay, but this thing goes to the sort of hyperbolic version of the same picture.
Yeah, I mean, if you want, I can even tell you how you define the map, at least in this case.
Sure, yeah.
Okay, so I'm just going to copy this for reference. Let's run over here. Okay, so here's our flat one. And what's our hyperbolic one? Now we've got 3 boundary components.
Also,
and more generally, you could do this. Oh, sorry.
Is the red the horizontal direction or the? Yeah,
so the red will be the horizontal direction.
Okay.
And so the way that you do this is that you, if you want, you could take a Voronoi decomposition of the surface, sort of based at the boundary curves. It's maybe the fastest way to say it. So you take, any point, you take its closest point projection to the boundary. So here, that's my closest point projection. Okay. This is my closest point projection. But then of course there are going to be a couple places, where all of a sudden, your closest point projection is, in multiple places. Okay. So like this. And, the set of places where you have multiple closest point projections will end up being a spine for the surface. And what you can do is you can sort of give weights to this spine, corresponding to the length of the projection of its edge to either side.
Okay.
Okay, and so for a surface with geodesic boundary, well, I'll say with curve boundary, I should say.
Okay.
The fact that sort of the hyperbolic structure is exactly captured by sort of this, I'll just weighted ribbon graph spine. This is a theorem of Fang-Luo. And if you sort of do this more generally, so with crown boundary, so something that looks like, possibly something like this, which is, what happens when you take complementary subsurface to an arbitrary measured lamination. This is a theorem of James and myself.
sorry, okay, so the map is you take the no. So how do you pick which okay, so the point is when you start with the quadratic differential, which is this picture on the left, you just decide to go to the picture on the right. So what does that have to do with the spine? Or are you going to tell us how to generalize the map to give the general case of the map? Or
yeah, so for the general case of the map, right, you take a surface with crown boundary and then you do the same picture. Maybe I should have done this all in red. Right, and then you can do a similar sort of picture, but then you're going to get a spine that looks like this. And that will, it'll capture the geometry of the corresponding quadratic differential. So
this is going from hyperbolic back to flat?
Yeah, from hyperbolic back to flat.
Okay. So you take this crown, you sort of subdivide it into pieces in this natural way, and then you sort of take flat versions of those pieces and glue them together.
Yes.
Okay. And the point is that this sort of hyperbolic geometry input is that you have to prove that sort of that weighted graph thing really is like a nice parameterization of the pieces.
Yeah, well, so you have to do that, but then you also have to be careful, because what does it mean to actually glue together a bunch of surfaces which have crown boundary to get like compact surface? Yeah. Right? Like that's like here's the thing, which is like I'm gonna somehow figure out a way to glue it all together so that the spikes are going to spiral all around the surface, and then they come back together.
Some like Bonahan cocycle or something.
That is exactly what we do. So we actually, I didn't say any of these words, but we generalize the Bonahan's machinery to arbitrary laminations, build a space of like shear shape cocycles, which sort of record this gluing data plus this spine data. And then you can put it all together to give a coordinate system for Teichmüller space for arbitrary laminations, with which you can then sort of do all of this.
Okay, hold on. I feel like that by itself is already quite a impressive thing. So you're saying you can make Bonahan shear coordinates on with respect to a lamination that isn't filling by adding in these purple what do you call them? Weighted ribbon spines?
Yeah. Yes.
And that works.
Yeah, it works. And moreover, so you can sort of, if you just want to build a coordinate system, or you can sort of do whatever you want, to be honest. But I guess the theorem, to state it precisely, I guess, is that I'll say for all measured laminations, lambda, there exists a space which I'll just call SH plus, and then I'll say something about what it is, such that you have a very natural homeomorphism. It's like stratified piecewise real analytic, if you want, such that Teichmüller space is coordinatized by this. And moreover, it is done so in a stab lambda equivariant way. And so this is stab in the mapping class group. And so if you have any lamination, like you can build coordinate systems based on it by completing it to a maximal thing, and then using Bonahan's notion of transverse cocycles. But if you do that, then like all of a sudden you've chosen something, right? You've chosen some sort of completion. And what you end up doing is that, well, as soon as you act by an element of the mapping class group, then you're acting also on that chosen completion, and so you're transforming the coordinate systems in a unnatural way.
Yeah.
And so so kind of the entire point is that this equivariance is sort of what allows us to build. And so this map that I was telling you about from Q&MG to Q&MG, right? This is in fact covered by a map at the level of Teichmüller space. This is really how you do it. But if you don't have equivariance, then it doesn't descend.
Yeah.
And so the equivariance is what allows you to push it down.
that's really nice. Yeah.
So this is the bit that's out, I'll say.
What's that?
This is already out.
Okay. This part, sorry. Okay, sorry, I'm not keeping up.
Yeah, no, sorry. There's a lot of stuff to fit in, and I sort of decided to elide over all of this to say the equidistribution result.
Yeah, no, it's all very cool. Okay, and then sorry to monopolize here, but there is a map going back from Q to P.
Well, so it's a bijection. I mean,
oh, you just prove it's a bijection.
We show it's a bijection.
The old-fashioned way. Okay.
Yeah.
Okay. Cool. Cool.
Well, I don't know. Let's thank Aaron again. No, I'm not sure if anybody else has a question. No.
Aaron, just let me say, I apologize. I know my students would have loved your talk. I hadn't really understood that they're going to a conference this weekend, but I hadn't understood that they were leaving this afternoon and they wouldn't be able to come. So so that's my fault. I've been, sleep deprived and not, but I have a new baby at home. But yeah,
well,
it did not occur to me. Thank you. It did not occur to me that they would be traveling right now and miss your talk. So I apologize for that. I'm glad it's being recorded though. I'm going to make them all watch it next week.
Okay.
Yeah, where is it? Where is it posted, the recording?
Oh, so I've been really lazy about not posting anything, but I will post them to the YouTube channel. So the Groups in Dynamics seminar has a YouTube channel.
Oh, okay.
And
how do I access that?
You could go to the RTG page, and then there's a link to it from there. Or just go to Google and type in like UTGD, I think.
Great.
Groups in Dynamics. Yeah.
Nice talk, by the way.
Thanks.
Yeah, very, very nice talk.
Thank you.
Okay,
Thanks,
well,
Aaron.
I guess that's it until next week. We have another talk next week. Okay, see you.